Alright, let's take a look at G-GMD.A.3. This is worksheet 1 and deals with prisms in particular and their volumes and the calculation thereof. So the earlier objectives were about developing the formulas to use, where they come from, how we use them. This is mostly just the doing, the calculating. But let me just speak about prisms for a minute. They have a very powerful characteristic, is that they have those two congruent parallel opposite bases. And so if you had an octagon like this and you stacked it continuously, you would fill that space, creating volume. Taking area and stacking it creates volume. Same idea here is that if we had a prism that looked like this, and we were able to get one slice, one cross section of that, and then stack it many times here, we would get the volume. So the formula for prisms come from that very idea. One base times that height. And so it doesn't matter whether it's a square base or a triangular base or a trapezoidal or hexagon or whatever. You just need to find that one base area and stack it for the height. Now that's why we reviewed all of those formulas and relationships. So here, for instance, volume is BH. But in this case, it would be the side times the side, that S squared, that's the area of one base, times the height. Over here, in this little guy here, we got a little b, we got an h here of that triangle, and maybe we'll call this big H to mean the height of the prism. So, you know what, that'll be confusing. Let's just call these different variables. Let's just call this x and y and normal h. I think we were about to confuse everybody. So volume is equal to BH, this base times that height. And because it's a triangle, it's 1/2 x times y. That would calculate the area of one triangle, that base, that height, divided by 2. And then I'm going to multiply it by the height. Do you see how this formula is getting customized each time to be the area of that shape times h, the area of that shape times h? Here, you would actually do this. You would take the area of the trapezoid and you would multiply that by the h here. So again, we got a couple of h's going on here, but this would be 1/2 base 1 plus a base 2 times that h, in this case is referring to the height of the trapezoid, times all of that, times the height of the prism. Lots of little things to keep track of, but this formula is so simple. What I always do, you can see me do it, I always put a box around my base calculations, and whatever I get there, I multiply it by h. We'll take a look at a few examples up close under the Elmo.
All right, this definitely focuses on calculation, so I'm going to go quickly again through the basic idea of a prism's characteristics. And the reason I say that is because if you want to know why the prism is BH, actually we write it big B like this. The reason we use it big B is that it represents the area of the base. So you and I have used B before, base times height, little b, but that would be a two-dimensional figure. This is saying find one base and multiply it by the height. The reason this formula works is the idea is that in one of these prisms, if you take that identical base that's identical on its opposite parallel face, as well as cross sections all throughout that are identical, all the way throughout, you would continue to get these shapes. The idea of stacking, I called it the stacking principle. So you create one and stack it so many times height-wise. And again, height is the distance between the two bases. It's not just from ground up. Okay, the height of a prism is always between the two bases. Here it's from ground up because the height is between the two bases. This way would be the height, and so on. So easy calculations. Let's roll through some of these just to give you an idea how to do them. So the area, again, of one base times the height. So I'm going to use the 6 and the 20. That would get me the 1, and then I would say my height is 14. And when I multiply these together, so I get the 120 times the 14 is 1680 centimeters cubed. Again, notice I'm dealing with a third dimension, and so in doing so, I'm measuring 3 dimensions, and so it's cubes that we're calculating here. We're looking at how many cubes fit into that. Here, a classic problem. This is a 13 here. This is a 5. We're missing this thing here. So, of course, if you haven't seen this enough times, you don't know what's going on then. So we get 12 here. So BH means, means 1 base times the height. The base is a triangle here, so watch what happens. I put in the triangle information. I like to put a little box around that to show all of that is B, and then my height happens to be 15. Now, where did the 1/2 come from? Well, my base in this case isn't a rectangle, it's a triangle, so I have to use its formula. 15 times 12 is 60. 60 divided by 2 is 30. 30 times 15 would be my answer. 30 times 15 comes out to 450. So it's 450 centimeters cubed. Here I have an equilateral, and I have different ways to solve this. I'm going to drop this down. That forms a 30, 60, 90 triangle. That cuts the 6 in half to be 3. The height of my triangle is 3 root 3. So here we go. Base times height. The base is a triangle again. And so to calculate it, it will be 1/2 its base times its height. All of that is just B, and then my height is 10. So base of 6, height of 3 root 3 divided by 2, because it's a triangle. And so I get 3 times 3 is 9, times 10 is 90 root 3 centimeters cubed. Let's take a look at maybe 1 or 2 more, just to do quickly to get a little more experience with it. Here, this prism happens to be a hexagonal prism, to see how the sides are opposite, parallel, and congruent. And so, again, it's just good old-fashioned BH. Volume is 1 base times its height, because, again, we're just going to keep stacking. I kind of made it an angle, but those congruent bases over that period of time. The base is found with 1/2 AP. Remember, the apothem times the perimeter, that would be the base, times the height, which in this case is 10. So I need to find out what the perimeter would be. That's not that hard. 6 is a side times 6, so the perimeter would be 36. That's not that bad. The apothem, I'd have to think about that, though. Let's draw out a hexagon here quickly and think about the apothem. Now, in the case of a hexagon, we know it's a 30, 60, 90 triangle. At least part of it is. If this is 6, this would be 3. This is the short leg, so this would be 3 root 3. So that's the apothem there, which would be 3 root 3. And then the 1/2. Again, this whole piece is calculating 1 base, because that 1 base is found by 1/2 the apothem times the perimeter. That gets me 1 base, and then I'm going to stack it 10 times. So I get, if I multiply all of that together, 3 times the 36 times the 10. Oops, let's do it again. 3 times the 36 times the 10 divided by 2. You get 540 centimeters cubed. Very cool. One last one I'll do, just conceptually. Because this is also a prism, even though it's a weird front plate here, it's not a trapezoid or a hexagon or something we recognize. The same idea works here, though. It's still b times h, because throughout that entire shape, you'll get that little shape all the way throughout. So what you can do is take the area of that base, which happens to be 28, and multiply it by the height. There's our height of 10. This is as easy as 280 centimeters cubed. Because the idea is you're going to take one of those and stack it that many times. It's cool stuff. I like prisms.